Okay, so I'll be kind of quick. Hi, everyone, any remaining people. Uh, so I decided this is kind of related to cancer modeling, but rather more like a spatial evolution project. I particularly chose it because this is something I recently finished, but that's among the very first problem I came to do, I thought of when I began working with Civ. So like when I first learned about Moran process from Mohammed and Civ, I was thinking of how can one make it into PDEs and really like deterministic dynamics type of things when you come to a spatial evolutionary models. So I hope I can address some of the novel features of the things I'm going to discuss today, and hopefully we'll have interesting comments about these things. And I've worked with a lot of people but however, I do evolutionary modeling works currently. Uh, Beside that, game theory, spatial evolution, I do a lot of cancer modeling currently at University of Minnesota. We have a research center. It's a new place, a therapy modeling design center. We do a lot of immunotherapy, cell therapy, and different kind of cancer modeling works. It's very closely working with clinicians and translational medicine people. So another reason for choosing the project is that to me, Civ was always the PDE guy. So I'm gonna talk some PDE for you guys. So I'm gonna skip some of the basic evolutionary modeling things. Just general interest for us would be the spatial evolution of in tissue structures, like most commonly important for cancer evolution. When you have a mutant, like an oncogenic or mutation appears, a driver mutant appears in the tissue structures, are going to spread. This is some type of breast cancer imaging, and we want to see how invasive it can be, and then the spatial patterns of it. Often the Moran process type of thing has been done. This is a older paper by Natasha and Mohammed and Satya. I often mention it in my talks. So you can actually, if you assume like a network type of structure and kind of unstructured mesh for your tissues, we can apply Moran type processes. These are constant population models where all the spaces are filled up, and mutants that's red can spread, advantageous mutant can spread and take over kind of some local area of the population, some sort of beginning of some type of clonal evolution. So a lot of literature has been spent on the last 20 years or so, even before that, beginning with Maruyama in 1974, that how the graph type of structure can represent these things. So the graph's network structure and the stochasticity are inherent to this type of modeling. We often talk about death-birth processes or birth-death processes, depending on where there are birth and death event proliferation, apoptosis events happening on two neighboring locations, depending on which one happens first. We distinguish the two models, and it happens to be, actually, they happen to be non-equivalent models. And there are some theoretical observations about fixation probability and stochastic quantities related to that. Something that I was always interested on is how we can connect these things to more standard understanding of the spatial modeling through PDEs. Normally, a lot of the PDE modeling, especially in ecology, is like Fisher-Kolmogorov-Pitofsky equation, like diffusion reaction equations, simple diffusion reaction equation for physicists. So S would be diffusion coefficient. S would be diffusion coefficient, D would be diffusion constant when these, and the phi would be the ratio of the mutants over resident population, the two competing type of population in a local area. So I'm assuming I'm having like these islands which are extremely small in size, There have a lot of mutants or population inside them, but still small in hydrodynamic limit in physics terminologies. Or it's basically meta population type models with very small sizes, physical sizes. So D would be related to the migration probabilities in and out, and S would be the differences between fitnesses of the two types. This is actually common when you have some type of dilute population, so you can actually move around to some extent and proliferate in the happily without when we can decouple movements from proliferation events. If you can do that, that should be there's a detailed discussion about this, but we can roughly prove that this is an okay approximation for in many simple scenarios. But when we have tissue structures, that's actually not really the case. Often this approximation very, very strongly assumed everywhere, but it might not be the case. At least we're going to theoretically investigate what would be the case when we have a Moran type process, when forget about the lattice structure, network structure of connectivity, but rather more importantly, that there is no void, there's no place to go. If you are going anywhere, you have to, somebody should die. So proliferation, like division, death, apoptosis, and movements are very coupled. And the coupling are basically through this birth, death, and death, birth prescription of the Moran process. They're like different ways of doing the dynamics. But going back to I want to see what it will be added to this model. How can I extend it in basically a crowded environment? I'm going to basically simplify all the naming of the project, of the talk, to how we can do how can write a spatial evolution in very crowded environments. And then finally, we want to also touch on, basically follow the standard literature of how to find the speed of the Fisher waves. These are the waves like a mutant appears, it establishes a colony, and it spreads with a constant velocity in the space of ecological habitats. Pretty much one of the very first things done in the theoretical evolution and ecology, introduced by Fisher, and if I recall correctly, Kolmogorov analytically proved it, and Pitovsky and Kolmogorov proved it analytically.
You are considering single equation.
I'm trying to include. I'm trying to extend Fisher-Kolmogorov equation while phi is the ratio of or something, basically something proportional to the mutants population.
The x is one dimension.
Then and x can be any dimension. No, x, it can be like 1 or 2 at least. And then the other quantity that's often derived is the boundary width. So if let's say in one dimension, this is the spatial dimension, this is the fraction of mutants. So I might have something like this, that going with the speed, the boundary between the fully saturated areas and 0 mutants, this boundary it also depends on the 2 parameters in the model, diffusion constant and the selection coefficient or selection advantage. So, and the third thing about the problem I'm gonna work on is that derivation of the stochastic Fisher-Kolmogorov equation for an evolutionary processes is actually extremely tricky. They're like part of it remains open problems. And then it turns out that for Moran process, it's actually much easier to approach those things. And while I'm deviating from Fisher-Kolmogorov equation a little bit, actually the derivation would I also gain the fact that I can exactly or more or less exactly derive my equations, especially the noise terms. So these are the things I'm considering. I'm assuming a constant population area, so there are no voids inside each island. They are connected with each other. I'm gonna look at some kind of hydrodynamic limit at the end, that these island sizes go scale like with very small island sizes, such that I can kind of recover some sort of tissue structure. And I look at the same thing in 2 dimension. For the first set of the equation I'm writing, I'm going to assume that the migration probabilities or migration rates from island to island is a constant. So, but later on, you can actually assume some sort of it becomes some sort of uh, gauge covariant vector field, the migration vector, if you want to assume a heterogeneous environment, but don't do it at the moment. So I'm skipping a lot of details for the model, but one important thing that makes it a little more exotic and more realistic is that I'm going to assume a 2-parameter model. I have birth rates and death rates separately. I have like a 2-component fitness model. So there is a birth coefficient, birth selection coefficient, and a death selection coefficient. So S represents the proliferation selection coefficient, differences between division rates of the 2 types, and Q represents the differences between the death rates of the 2 types. Migration would be just replacing. So somebody died, like the exact same Moran process in meta population model. I have 2 islands. I choose somebody to die if that's a deathbed process. Either somebody inside the island or somebody outside the island. Neighboring islands will proliferate and replaces that individual. Yes, migration is completely coupled. No, there is no swapping. Migration, it can be. I just didn't have time to do more than 2 processes. Actually, you can do all kind of things. It's going to be extremely interesting to like swapping and other stuff. I love the swapping idea you have introduced many years ago. That can be like a type of actual migration in crowded environment that can be added to this type of work. So these are like I'm setting up very basic stuff. So what's that? Crowded means that the population is constant, so you cannot go anywhere other than unless you can actually kill somebody, replace it. And what Natasha mentioned is that there's another option. You can actually change the update rules such that you can kind of decouple the proliferation and death and migration by the fact that if somebody's moving, it's kind of pushing others around. So that's one way with the swapping. Like that's like literal random walk in crowded environments. Like that's another thing that could happen totally. So at the end of the day, you can derive in weak selection, and for small enough selection, birth coefficient, birth selection coefficient, death selection coefficient, you can see that there are some very interesting features. The Laplacian term, like the Brownian motion term, actually has a dense. And this phi is, I have to keep reminding us, myself included, phi is the fraction of mutant in each location. And that's the function, and it should, at the end of the day, it's location and time dependent. So each index of I in the continuum limit is gonna be replaced with an X. And so it actually has a phi in front of it. So in other words, you have like a component. You have a small component that's density dependent in a sense. Like a diffusion constant is somewhat density dependent. More importantly, or more exotically, there is this phi bar. This phi bar is actually overall density, over like average density of the mutants all over the population. So you actually have a long range or a mean field term in the same diffusion term that actually appears for death-birth process in this form.
And the question is, those are actually fixed laws, right? So you do understand that equation, the way you wrote it, assumes that these constants, right? Because the classic fixes the divergence of d times the gradient of phi. Why, therefore, if you actually multiply your d by that expression that is a function of space and time, I'm assuming, why do you still have the Laplacian? It should be the divergence of that term multiplied the gradient of phi, right?
So I'm just looking at the leading terms of a spatial terms. It happens to be a Laplacian in front of a function of densities. It doesn't come from this divergence term necessarily. All these symmetries that I have from a Brownian motion type of thing, a lot of them are broken.
But when you are speaking the density dependent.
So there happens to be a density dependent.
So it's fixed law is the divergence.
Yes. If I'm correct, the fixed law is not applicable here, I think.
So then how do you
I just literally derive it from the stochastic process that defines the Moran process on this meta population structure, like directly derive it from there.
Because this kind of pattern you are typical obtaining from hydrodynamic reasons.
Yes, I do write down the changing these are beginning with the discrete type model. I write down the changes over time for mutant frequency at some particular island. These are transition probabilities. Like I substitute transition probabilities, very nonlinear looking, and we go to a hydrodynamic limit, etc., etc. And this would be the.
But you are starting from a model that is actually very localized. So I would rather not take the limit and stay. It's exactly actually that's the equal to that Natasha was talking. You want to stay in the discrete space. It's allowing you more flexibility rather than actually go to the Laplace, go to the diffusion equation. I will not take the limit, but anyway.
So let us discuss it a little later. I agree with you that I'm actually the results I'm gonna report are from the discrete model from the island. However, wait. However, I can show you the numerical result from a discrete model, but there is analytical results from the PDEs, and they do actually match for the Fisher wave speed. Okay, I would be very happy to talk about issues with this type of hydrodynamic limit stuff. I would be more than happy to talk that. So similar, bit weirder, somewhat weirder look can be derived and kind of different for the Bether process. You can have related to the depth selection coefficient. You can have a Laplacian squared term. And sorry, oops. I was gonna mention also a paper on PRE that's published in 2017 that's addressed by Bahram Houshmandzadeh in Grenoble. They actually derived a simplified version of these things, more similar type of model with a lot of restrictions. So I would be happy to fight over the hydrodynamic limit stuff. So some numerical observations would be that if I assume only selection coefficients and being on the proliferation terms and the death rates are constant, then it turns out that the Detbert process have approximately constant Fisher wave speed. So this cone type diagrams are the space-time plots where they have 100 islands of size 100. So 100 island total population are 10,000, 100 times 100. And I'm beginning with one mutant and a very small number of mutants in the middle island, island 50. And it takes almost this much time. And this is time, and this is a space, basically. It takes this much time to pretty much fill up an island, which are these yellow regions. And then the mutants are spread until they fill out the whole space. So the speed of the spread would be the slope of these two slopes. For Fischer Kolmogorov, it turns out that the slope is just a little less than the death birth with a similar selection coefficient. For the birth death, you can see slope is a little bit changing, so it's kind of deaccelerating a bit, and it's also a little bit slower than death birth and Fischer Kolmogorov on average. If I do average speed all over this deaccelerating wave, it's actually on average a little bit less than death birth and Fischer Kolmogorov. So the death birth and birth death processes are not just locally different, they have a little bit of different fixation probabilities. They also have different Fischer wave speeds, a little bit different, like I guess more than few percent. But I'm very curious, and my general philosophy to do these things is that we often don't know what type of update rule to apply for example, for a cancer mutation and a particular tissue structure, etc. Probably looking at the how these patterns of invasive patterns of tumor is growing can be leading us to identify the two different fitnesses that get death changes in death rates and changes in proliferation rates, and also things incorporated with like with the spatial structure like the diffusion constant, etc., would probably tell us that what type of processes, some birth death or death or something in between, is happening for that particular oncogenic mutation or some particular cancer cell line. So one can extend some heuristic argument. One can extend this and work out Fischer wave speed for death birth and birth death that has to do with, it has the two fitness coefficient terms, birth minus death, and however, it also has the overall frequency of mutants, average frequency of the mutant over all the population inside it, assuming that the sizes are extremely large. So and then these dots here are numerics, and the solids are sorry, the other way around. The dots are these formulas, and then the solids are numerical simulation, and it turns out that our PDE things are, at least for as long as it's gonna estimate the Fischer wave speeds, it seems to be working. So one last thing, and I'm gonna finish, is that we can also introduce a spatial heterogeneities. We can introduce left and right differences for migration, a kind of a bias in one dimension, in addition to having a general migration potential, whether a mutant gonna stay in that location or resident or gonna move out. And also you can introduce it in two dimensions. You can have two biases, one along y-axis, one along x-axis, and also the overall migration potential of staying or not staying. And at the end of the day, you can, I'm not reporting the PDE that comes out of this thing. It's in the hydrodynamic limit, but it's doable. It's actually very, very messy looking, but you can actually look at one specific case, that's isothermal graphs. This is not exactly to do what our PDE is, but it tells you that the bias, you can define an overall migration vector. That's general the vector of your biases in 2 dimension is a 2-dimensional vector, and also the mu, the scalar potential that tells you that what is my migration potential locally. Is it at location X? Mu of X tells I'm going to move out with probability rate mu. And then with one minus mu, I'm going to stay there. So the gradient of mu plus these two-dimensional vector, let's say 2-dimension, would be some sort of migration flow vector that is divergence-less. If only for isothermal graphs where basically representing some graphs that is often used in network evolution models, and that's when the total probability for incoming migration is the same as outgoing migration. And nothing very tricky about it, but I thought it's a very neat little neat observation that the vector J that represent your migration as a little vector field in your space, in your 1 or 2-dimensional space, actually have some sort of gauge field behavior. So mu, the migration potential, plays the role of a gauge field that can change J. So a lot of other directions are ongoing on these things. Is looking at the spatial like heterogeneous structure and PD and things that might come out of these considerations for unstructured network structures, comparison with real tissue growth models, because it does introduce a very simple model, two to three compartment, 3-parameter model that one can fit for, and also we are also looking at the gradient with environmental heterogeneities, and when the fitness varies along the population, when basically the resources across the population are different. So that was very quick talk going over. Thanks for staying until the end.
Okay, thank you. Any questions?
Mhm.
So first of all, I really enjoyed your talk.
Thank you.
But if you are